All right, if you have a bit of a look at that, and just while you're doing that, I'll upload my solution just so you, because I don't think you've got this question either. So this is actually the quiz 2 from last year, made a little bit more difficult because I thought it was way too simple for last year. All I did was change, so where you've got this 1 here, I changed that to changed it from a 2 to a 1. Otherwise it was trivially simple. Okay, so have a look at that, and I'll just grab that quickly for you, upload it. And you can even start having a go at solving it if you like. Okay, so I put that in Teams, and the link's in the chat. So please try not to jump too far ahead. What kinds of things are you thinking about when looking at this type of problem? What are you thinking you're needing to do? Any ideas? Could AB be a 2-force member? Yeah, good thinking. BC and BD a 2-force member. Okay, yeah, so Nicholas says can't be a 2-force member because it has a force applied in the middle. Looking at this thing, so you might be tempted to think that it's a 2-force member, but as Nicholas commented, because we've got this force applied in the middle of it, it's not a 2-force member. If the force was applied out here at B instead of E, right, if the force was applied out here, if we apply the force out here at B, then yes, then it would be a 2-force member, right? Because we've only got, we would only have forces applied at B and A, right? But in this case, the force is applied somewhere else. All right, so I think the other thing was BC and BD, 2-force members. Yeah, so these are cables. BC and BD are both cables. So we know, we're going to know the direction of the forces in those cables. Yeah, so thinking about the reaction forces here. So I think we're looking at A. I think it's told that we have a ball and socket joint at A. So if we have a ball and socket joint, then the thing is free to move, to rotate in any direction around that point, but it can't move away. Okay, so no moment reactions at A, but 3 force components. All right, so what kinds of approaches to solving this problem? It's obviously an equilibrium problem. So we've got to use some equations of equilibrium somewhere. What other things might we be thinking about making use of? Direction vectors, yeah. All right, so looking at, all right, so we've got these forces going off at some weird angles. So you might need to look at using your direction cosines to get the force at B and C and the force along BD in some kind of a vector form. Yeah. And you also might be thinking that you might have to do a cross product somewhere when you calculate a moment. All right, so let's have, I actually solved this 3 different ways. And I've posted in Teams, by the way, just quickly, let's go to Teams, where's Teams? Right here. Moment about y-axis at A. Yeah, that's a good suggestion. I think I did something along those lines. If we go to general and in, whoops, in post, so you can see Fatma's uploaded her solutions to the tutorial problems and also some final exam problems from last year. And I've also uploaded my solutions to questions 1 to 5 on Canvas. And I think the original ones that were there, the other tutor, Mubarak's solutions. And if you look at them, they're all different. All 3 are different. But we all come up with the same answers. So in most problems, there's more than one way to solve them. In those simple 2D equilibrium problems, usually they all take the same form and look pretty much the same. You know, draw a free body diagram, take moments about a point, use the moment equation, and then use the two force equations. They all, you know, most solutions look much the same. When you get to 3D problems, many more options for how you solve the problem. Okay, so what I've suggested to you here in the Teams chat is whenever you do these problems, try and force yourself to do the problem again using a different method or approach, right? Or using a combination of what you've done and something else. All right, so let's see what I've done here. Okay, so usual thing, you could do this problem without drawing a free body diagram because it's pretty simple, you know, and a lot of people would draw on the question, right? When you're doing solutions for quizzes, and if you're doing a problem like this from scratch in a design exercise, then you've got to draw the free body diagram. So please get into the habit of doing that. All right, so I've just drawn my free body diagram there, just for the geometry. If you're using a pad, like a tablet or an iPad or a Surface Pro or something like that, one tip is to use the question. So I told my tutors, my students in my tutorial this. You know, what I'll do is actually trace over the question and then cut and paste and use that in my solution. I can do that because well, in this case it wasn't my drawing, but you know, in a quiz you can save yourself a bit of time drawing a nice free body diagram just by tracing over that. If you're doing it on paper, like if you're doing a paper-based exam, I don't have any here. But you can see this background on my thing here, the grid paper. Sometimes that graph paper that you get in a A4 grid book is quite thin. So you can just lay it over the top of your question and just trace over the, you know, at least the shape of the thing. Right? So you can draw for yourself good free body diagrams. And the other thing to do is, as I showed, it's a bit hard in this. I need a white background. Right. If you get yourself a set of set squares like this, you can very quickly draw free parallel lines. Right? Draw that one, and then slide this along, and draw your next one. Slide it along, draw your next one. So you can quickly draw. Right? If you have to draw these three lines, right, and even these lines up here, you can quickly draw them using your drawing instruments like this. Okay, probably quicker than really you can try and doing them roughly freehand. Right? So the payback in maybe the 30 seconds longer that it takes you to draw your lines with this rather than freehand, the payback is worth the effort. Right? Not only because I give you marks for doing a good free body diagram, but it helps you to understand and solve the problem better. All right. Okay. So then we said, yeah, so we're going to have some forces along these cables. So let's put those in. We don't know what they are. Let's label them TBC, TBD. And at A, we've got reactions. We don't know the directions. So maybe assume positive directions for all of them or positive sensors for all of them. Now you've got free body diagram. You can start launching into equations of equilibrium, or you can try and work out your cosine, your direction cosines for these angle forces here. But that's in the chat. Jonathan said take moment about y-axis at A. Yeah. So let's have a look and see what would happen if we did that. So that's a good suggestion, and I'm pretty sure I did something like that in one of my solutions. What would happen if we do that? How many unknowns will we have in the equation? 1, 2, 3, 4. If we take the suggestion, take moments about the y-axis through A, how many unknowns are we going to get in that equation? So one person says 2, someone says 1. Okay, so yeah, so we're going to have 2 unknowns, aren't we? So both TBC and TBD will both have moment effects about the y-axis through A. Okay, so we've got one equation with 2 unknowns. So we can't solve for anything yet. That's okay. Just go to the next equation. What might we do next? Start looking at force equations, start looking at direction cosines. Let's have a look at what I did. I can't remember which one I did first. So this one I did the direction cosines first. Right, so what I did was to find the to express these 2 unknown forces using their direction cosines. Right, anyone need any further clarification or discussion on this? Happy with finding your direction cosines? Okay, so I've got a few questions here. All right, so let's take a look at, so why the value is negative? Yes, because of their directions, right? So if we look at, let's take TBC, because that's the one I've done first. So this is the direction that we want, right? This direction from B to C, okay? So we do, if we're going from B to C, then it will be C, coordinates of C minus B, okay? So here it's in the X direction, 0 minus 6, so it's minus 6. The other way to think about it is to just look at the direction of the force, right? So right, we can see that TBC is going in the negative X direction. So we know that it's going to be in the I direction, it's going to be a minus something times I. So, so this is just the unit vector in direction of BC multiplied by the magnitude of BC. Yeah. Yes, that's right. And I think we're running out of time, but in one of my other solutions, I simplify this down even further. So talking about direction cosines and things sounds a bit, you know, mathsy and vectory and whatever, and may not be quite sure, but all we've done is to find the unit vectors along X and Y directions, or the components of this force along X and Y directions, X, Y, and Z directions. Right? And this is the maths way of writing that. Right? The mistake that I often make when I'm doing these problems is I forget to divide by the magnitude. Right? So I'll just leave it here as 6I2J plus 3K times, and I forget to divide by the magnitude. So that's a mistake that I often make. So I've got to watch out for that. So you may have that problem as well. Right. So and these numbers here, right, these are just the cosine of the angle between TBD and X. This one's the cosine of the angle between TBD and the y-axis, and so on. Okay, so I've just repeated those on the next page for reference. All right, so now I said, all right, let's take moments about AZ. I could have taken moments about AY, as was suggested. Any idea why I might have taken moments about AZ instead? Well, if we'd taken values about the y-axis, that would have included the known, right? positive versus negative moment. Yeah, if that helps you. But no, the reason why I took moments about the z-axis through A instead of the y-axis as we were looking at before, right, is because it will simplify my relationship between TBC and TBD. Right? So our discussion before was that if we took moments about the y-axis, we're going to have one equation with two unknowns. Right? If I'd taken moments about the y-axis through A, I would have had TBC, TBD, and the 800 Newton force. Right? So my equation that relates TBC to TBD would have included this 100 Newton times 3. Right? Whereas, right, because 800 is parallel to Z, when I do this equation, let me put it up for you now, what I end up with, right, is simply TBC is equal to something times TBD. Right? So when I go to my next equation and I have to substitute, right, so I'm thinking ahead to, right, I've got one equation with two unknowns here. My next equation is probably going to have two unknowns. And if it does, then I want to make it easy for me to do the algebra. Okay. So let's see what I did next. So next I did some of the moments about AY. Okay, so in this equation, right, only these two things are going to appear, but it will, the 800 Newton will also appear. Right? So that's okay. So I've rushed through this cross product stuff a bit. Okay, good question. What would I recommend for a student who's not so strong with the cross products? We'll get to that in a second. But what I really do encourage you to spend some time trying to get on top of the vector maths. You know, I think I've said to some of you before, you know, it's actually quite a while since I've done had to do this vector stuff. You know? So I've just had to go back. Oh, right, that's how you do that. Because mostly I don't use it. Mostly I get around it. Because mostly I don't need to. Right? But what the vector stuff is really good for is, you know, if you're wanting to put things into MATLAB, for example, and use MATLAB to do your maths for you. And then using, you know, if you look at some of the solutions that have been provided that I got from the previous subject coordinator, they're just straight from the solutions manual, and they're kind of in vector format. So that's one of the reasons for making sure you can do this. But anyway, let's move on. So just doing the maths. So you can see in this equation where I've got the two unknowns, TBC and TBD, right? My substitution is really easy, right? It's just TBC here becomes 0.5159 TBD, and I just shove that in, right? And I can easily do that algebra. Right? And that gets me those two values. And then you can just do the sum of the forces. All right, so there's my final answers to that one. RAY equals 0. Do these values make sense? Right, so you can have a look at that and try and think through, and you know, in the fact that we've got RAZ is 400. So let's do this one just quickly. RAZ is 400. Does this make sense? Right? If we take moments about point B here, RAY we found was equal to 0. This force goes through point B, doesn't cause a moment. So we've got 800 times 3. So we're going to need RAZ times 6. So it's going to need to be half 800, right? So 400. So do those kinds of thinkings with your solution. So I want to try and get to the alternate solution. All right, if we take moments about point B, z-axis, we can get RAY is equal to 0 straight away. All right, so the person, if you're not so good at the vector notation and all that stuff, this is my solution. Take moments about B in the Y direction. So here we're going to, so RAY is 0, so we're left with RAZ. You can find that one straight away. So for those who aren't strong in the vector mechanics, what you do need to be strong in is a really good understanding of basic moment calculations. Right? Right, so here, I have to take moments about point B, y-axis. The only thing that's going to cause a moment is this 800 and this RAZ. So now if I do some of the forces in the Y direction, so that's this way, the Y component of TBC must be equal to the Y component of TBD, because we already found that RAY is 0. If you need to rush off, please do so. I won't be offended. Sorry, I've gone a little bit over time. Now, I said an easier way to think about the direction cosines is, you know, when we have just a triangle, like this, and we say, let's say that's 2 and that's 7. In fact, let's not do that. Let's do 3, 4, right? If we have a triangle like that, and right, that's our force, we know this is 5, right? How do we know that? Because it's 3 squared is 9, plus 4 squared is 16, square root of 9 plus 16 is 25, square root of 25 is 5. So that gives us that. Right? So if we call that F, and along here Fx, what's Fx equal to? Right. Fx is equal to 4 over 5 times F. Okay. And Fy will be 3 over 5 times F. Right? So when we're doing direction cosines, this is all we're doing, but in 3 dimensions. So instead of having only 2 terms, right, so here we've got, so let's go Fx equals 4 over square root 4 squared plus 3 squared. So these values here, 3/5, 4/5, they're your direction cosines. Okay, so someone said, why haven't I included RAX? RAX in what? Why did I not include RAX in what? What do you want me to include RAX in what I've done so far? Moments of BY? Okay, so RAX passes through point B. Right? So therefore it will have 0 moment about an axis through point B. Cool. Right, so there's my direction cosine for TBCY. Same thing for direction cosine for TBD. So all I've done is just use Pythagoras in 3 dimensions instead of 2. And I get the same relationship between TBC and TBD that I got before. now I can take moments about AY. Here I've got TBCZ and TBDZ. So you need to be able to visualize the components that are causing moments. That all equals to 0. So again, I needed to find the direction cosines, and the direction cosines are just a fancy way or mathematical way of finding the components of the force in the direction. Right? And in 3D, you just got to do it like this rather than what you were used to for 2D. 6 squared from 6 squared. If you want to hang around, I'll just finish this and get back to you. So heat change just we're 6, right? So these are just I got these in the same way that I got the direction cosines to start with. Right? So if we right, so if this force was just up to here instead, right? We could just do, the x component would be 6 over 3 squared, square root of 3 squared plus 6 squared, right? But in this case, we've got the force at an angle to all 3 axes, right? So we need all 3 sides of the rectangle rather than the 2 sides of the triangle. Right? And we end up with hopefully the same values that we had before. Okay, so there's my solution without any obvious IJKs, any obvious direction cosines, no cross products. So this is, if you'd asked me to do this 6 months ago, this problem, this is how I would have done it, right? But because I'm now teaching this subject, and I need to teach again this vector stuff, I need to do solutions that include the vector stuff. But yeah, so Josh, I agree. I prefer this way because most times this is all I need, and most time I can do this without having to look up any textbook or refresh my memory on any equations. This is doing it this way. I can do this off the top of my head without looking up anything. It looks simpler, right? But it really, as I said, you've got to have a really solid understanding of the basics of especially moments. Right? And then, so this is my way, right? This is the dummies way, right? Keep it simple, stupid way. Here's another solution. Now this is the clever solution. Right? So here, so in our 2 previous solutions, it took us 2 equations to find our first unknown. Right? You can find one of your unknowns, either TBD or TBC, straight away with just 1 equation. Right? Now, if you don't get this way, don't worry too much. But what we can do, if we look at all of our forces here, so all of these 3 forces pass through a point. TBC passes through point C. So if we define an axis from A to C, like that, and we take moments about that axis, then we can solve for TBC straight away. You see that? Sorry, not TBC, TBD. Right? Because if we take moments about this axis AC here, TBC passes through point C, that has no moment effect. Our 3 reaction forces down here all pass through that axis, so they have no moment. So all we're left with is 800 and TBD. Sounds simple, then the maths gets messy. So I'm just going to jump to the end. Okay, so you need to find the direction, right, the direction vector for AC, so UAC. Then you need to find the position vectors from the force to the axis. So, and then you need to find the force as a vector. Right? So that's what that looks like. And we get TBD, same as before. So that's the clever maths solution method. All right, I've gone over time. Sorry about that. Hopefully all of that was helpful.